Tonight we're going to confront one of the most unsettling questions in all of physics. The electron in an atom carries a negative charge. The nucleus carries a positive charge. Opposite charges attract. You learned that in school. So why doesn't the electron just fall straight into the nucleus? It should spiral inward, crash, and that would be the end of the atom. The end of matter. The end of you. Every atom in your body should have collapsed in a fraction of a second. And yet here you are. Something is preventing that catastrophe, and it's not what you think. The electron isn't orbiting the nucleus like a tiny planet. It's doing something far stranger. And when you ask what the electron actually is, what it's made of, the answer is so bizarre that it forced physicists to abandon nearly everything they thought they knew about reality. If you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing, but it makes a huge difference. Now, let's begin. Let's start with something you already know, or at least something you think you know. Atoms. Everything around you is made of them. The screen you're looking at right now, the air you're breathing, the bones in your hands, the water in your cells, the chair you're sitting on, the floor beneath it, the ground beneath the floor, all the way down to the molten iron churning at the center of the earth. Atoms. Roughly 7 billion of them make up a single human body. They are the building blocks of matter, the basic units of chemistry, the alphabet from which every material substance in the known universe is written. And every single one of those atoms has the same basic structure. A nucleus at the center, dense and positively charged, surrounded by electrons, light and negatively charged. The nucleus contains protons and neutrons, tightly packed together in an incredibly small volume. The electrons exist somewhere outside the nucleus, much farther out. That much you probably already know. But here is what most people never stop to think about. The protons in the nucleus carry positive electric charge. The electrons carry negative electric charge. And one of the most fundamental laws in all of physics, a law that has never once been violated in any experiment ever conducted in the history of science, says that opposite charges attract each other. Positive pulls on negative, negative pulls on positive. The force between them is described by Coulomb's law, published by French physicist Charles-Augustin de Coulomb in 1785. The law says the electric force between two charged objects is proportional to the product of their charges divided by the square of the distance between them. The closer they get, the stronger the force becomes. Double the distance, and the force drops to 1/4. Halve the distance, and the force quadruples. Bring the charges very close together, and the force becomes enormous. So think about what this means for an atom. The electron is negatively charged. The nucleus is positively charged. The electron is separated from the nucleus by a very small distance, roughly 1/10 billionth of a meter. At this distance, the attractive electric force is immense compared to anything you encounter in daily life. If you could somehow feel the force pulling a single electron toward a single proton at atomic scales, scaled up to human experience, it would be staggering. This force is pulling the electron straight toward the nucleus, every moment, without pause, without exception. So why doesn't the electron just fall in? This isn't a trivial question. This isn't a minor curiosity. This is one of the most important questions in the history of physics. Because if the electron did fall into the nucleus, atoms would not exist. Chemistry would not exist. Molecules would not form. Solids, liquids, gases, none of them would be possible. Stars would not shine, planets would not form, life would not exist. You would not exist. The entire observable universe, all 93 billion light-years of it, with its 2 trillion galaxies and 200 billion trillion stars, all of it depends on the fact that electrons do not fall into nuclei. Everything hinges on this, and for a long time, physicists had no idea why it didn't happen. Let me take you back to the early 1900s, because that's when this problem became impossible to ignore. In 1897, the English physicist Joseph John Thomson discovered the electron. He was studying cathode rays, streams of something that flowed through vacuum tubes when you applied a voltage. By carefully measuring how these rays bent in electric and magnetic fields, Thomson determined that cathode rays were made of particles, tiny, negatively charged particles with a mass far smaller than any atom. He called them corpuscles at first, but the name electron, which had been proposed earlier by the Irish physicist George Johnston Stoney, eventually won out. Thomson's discovery was extraordinary. For centuries, scientists had debated whether atoms were truly indivisible, the smallest possible units of matter. Thomson proved they were not. Atoms contained something smaller. They contained electrons. But this raised an immediate question. If atoms contain negatively charged electrons, they must also contain positive charge, because atoms are electrically neutral overall. The negative charge of the electrons must be balanced by an equal amount of positive charge somewhere. But where was the positive charge, and how was it arranged? Thomson proposed a model. He suggested the atom was a sphere of uniformly distributed positive charge, like a ball of positively charged pudding, with electrons embedded inside it, like raisins in a plum pudding. This is why his model became known as the plum pudding model. In Thomson's picture, the electrons sat at equilibrium positions inside the positive sphere. The positive charge pulled on them from all directions, and they settled into stable arrangements. The model was reasonable. It explained atomic neutrality. It was consistent with what was known at the time, and it seemed to provide stability. The electrons weren't orbiting anything. They were just sitting in place, held there by the surrounding positive charge. But Thomson's model was wrong, and the experiment that destroyed it was one of the most famous in the history of science. In 1911, Ernest Rutherford, a New Zealand-born physicist working in England, conducted an experiment with his colleagues Hans Geiger and Ernest Marsden. They fired alpha particles, which are helium nuclei consisting of 2 protons and 2 neutrons, at a thin sheet of gold foil. Alpha particles are relatively heavy and positively charged. They move fast. If Thomson's model was correct, the positive charge in the gold atoms was spread out uniformly across the entire volume of each atom. An alpha particle passing through should experience only small, gentle deflections from this diffuse charge. It would be like rolling a bowling ball through a room full of cotton candy. The ball might wobble slightly, but it would pass straight through without much trouble. And for the most part, that's exactly what happened. Most alpha particles went straight through the gold foil with barely any deflection at all. But some of them didn't. Some alpha particles bounced back at large angles, and a small fraction, roughly 1 in 8,000, bounced almost directly backward, coming back nearly the way they came. Rutherford was stunned. He later described it by saying it was as if you fired a 15-inch artillery shell at a piece of tissue paper, and it came back and hit you. The plum pudding model could not explain this. If the positive charge was spread out over the whole atom, no alpha particle could ever encounter a concentration of charge dense enough to deflect it backward. The only explanation was that the positive charge was not spread out. It was concentrated in an incredibly small, incredibly dense core at the centre of the atom. Rutherford called this core the nucleus. The numbers were extraordinary. The atom itself has a diameter of roughly 1/10 billionth of a metre, which scientists call 1 angstrom. The nucleus, Rutherford determined, has a diameter roughly 10,000 to 100,000 times smaller than that. If you scaled the atom up to the size of a football stadium, the nucleus would be about the size of a small marble sitting at the centre of the 50-yard line. Everything else, the vast majority of the atom's volume, was empty space. The electrons were out there somewhere, far from the nucleus, occupying the rest of that enormous volume. This was a radical new picture of the atom, but it immediately created a devastating problem. Rutherford's model looked a lot like a miniature solar system. The nucleus at the centre, massive and positively charged, playing the role of the sun. The electrons orbiting around it, light and negatively charged, playing the role of planets. The electric force pulling them toward the nucleus, playing the role of gravity. It was a beautiful and intuitive picture. It felt natural, it felt right, and it was completely, fatally wrong. The problem was not with the idea of orbits in general. Planets orbit the Sun just fine. They've been doing it for 4.5 billion years, and will continue for billions more. Gravity pulls them inward, their orbital velocity carries them sideways, and the result is a stable elliptical path. Planets don't spiral into the Sun. They maintain their orbits indefinitely, assuming nothing disturbs them. So why can't electrons do the same thing? The answer involves electromagnetism, specifically the work of the Scottish physicist James Clerk Maxwell. In the 1860s, Maxwell unified electricity and magnetism into a single framework, producing 4 equations that describe all electromagnetic phenomena. Maxwell's equations are among the greatest achievements in the history of physics. They describe how electric charges create electric fields, how moving charges create magnetic fields, how changing magnetic fields create electric fields, and how changing electric fields create magnetic fields. They also predict the existence of electromagnetic waves, self-propagating disturbances in the electric and magnetic fields that travel at the speed of light. Light itself is an electromagnetic wave, so are radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays. All of them are solutions to Maxwell's equations. And Maxwell's equations make a very clear, very unambiguous prediction about charged particles that are accelerating. They radiate energy. Any charged particle that accelerates, meaning any charged particle that changes its speed or direction, must emit electromagnetic radiation. It's not optional. It's not something that only happens sometimes. It's a fundamental consequence of the theory. Accelerating charges radiate, period. Now think about what this means for Rutherford's atom. An electron orbiting the nucleus is constantly changing direction. Even if its speed stays the same, its direction of motion is constantly changing as it follows its curved path around the nucleus. A change in direction is acceleration. So according to Maxwell's equations, the orbiting electron must radiate electromagnetic energy continuously. But energy has to come from somewhere. The electron can only radiate energy by losing its own energy. As it loses energy, it slows down. As it slows down, it drops into a lower orbit, closer to the nucleus. But in a lower orbit, the electric force is stronger because Coulomb's law says the force increases as the distance decreases. The stronger force means the electron orbits faster. It's accelerating more, so it radiates even more energy. It drops even lower. The force gets even stronger. It accelerates even more. It radiates even faster. The whole process is a runaway feedback loop, a death spiral that accelerates as it progresses. How long would this take? Classical physicists calculated the answer, and it was horrifying. For a hydrogen atom, the simplest atom, consisting of 1 proton and 1 electron, the electron would spiral into the nucleus in roughly 100 billionth of a second. That's a tenth of a billionth of a second. Essentially instantaneous. Essentially instantaneous. Every hydrogen atom in the universe should have collapsed in the first fraction of a second after it formed. And since more complex atoms have the same basic structure, nucleus plus electrons, the same logic applies to all atoms. All matter should be unstable. All atoms should collapse almost immediately after formation. Nothing solid should exist. No molecules, no chemistry, no stars, no planets, no life. And yet, here you are, made of atoms, stable atoms, atoms that have existed for billions of years. This was the crisis facing physics in the early 20th century. The 2 most successful theories in all of physics, Newtonian mechanics and Maxwellian electrodynamics, when combined, predicted that atoms could not exist. Not that they were unlikely, not that they were unstable over long time periods. They predicted that atoms were impossible, that matter itself was impossible. The theory said atoms should collapse in a billionth of a second, and yet atoms obviously existed and had existed for billions of years. The discrepancy between theory and observation was not a small numerical error. It was a total, absolute, catastrophic failure. This is important to understand, because it shows that the problem was not a gap in knowledge that could be filled by a small adjustment. It was not a case where the existing theories were approximately right and just needed fine-tuning. The existing theories gave an answer that was wrong by something like 26 orders of magnitude. The predicted lifetime of an atom was about 10 to the minus 11 seconds. The observed lifetime was effectively infinite, at least billions of years, which is about 10 to the 17 seconds. The ratio between prediction and reality was roughly 10 to the 28. The observed lifetime was effectively infinite, at least billions of years, which is about 10 to the 17 seconds. The ratio between prediction and reality was roughly 10 to the 27. That's a 1 followed by 27 zeros. No small correction can fix a discrepancy that large. Something fundamental was wrong with the classical picture. Some physicists tried to find ways around the problem within classical physics. Maybe the electron wasn't really orbiting. Maybe it was just sitting still, hovering at a fixed distance from the nucleus, held in place by the electric force. But that doesn't work either. A stationary electron in the field of a nucleus is in an unstable equilibrium. The slightest disturbance, and disturbances are always present, would cause it to fall inward. It's like balancing a ball on top of a hill. In theory, the ball can sit at the very top. In practice, any tiny push sends it rolling down. And even if you could somehow keep the electron perfectly still at a fixed distance, that would create other problems. A static model can't explain the spectrum of light that atoms emit, which was already well measured by this time. There was also the question of what happens when atoms interact with light. By the late 1800s, scientists had carefully measured the light emitted by hot gases of different elements. When you heat hydrogen gas until it glows, it doesn't emit white light. It emits light at very specific colors, very specific wavelengths. Each element has its own unique pattern of spectral lines, like a fingerprint. Hydrogen emits a red line, a blue-green line, a violet line, and several others in the ultraviolet. These wavelengths had been measured with extraordinary precision. In 1885, a Swiss mathematician named Johann Jakob Balmer found a simple mathematical formula that predicted the wavelengths of hydrogen's visible spectral lines. The formula was empirical. He found it by trial and error, not by deriving it from any physical theory, but it worked perfectly. Every visible spectral line of hydrogen matched Balmer's formula. Later, the Swedish physicist Johannes Rydberg generalized the formula to include ultraviolet and infrared lines as well. The Rydberg formula expressed the wavelengths of all hydrogen spectral lines in terms of two whole numbers, just integers. The wavelength of each spectral line corresponded to a specific pair of integers, and no other wavelengths were emitted. This was deeply mysterious. Why whole numbers? Why discrete wavelengths instead of a continuous spectrum? If the electron could orbit at any distance and gradually spiral inward, it should emit radiation at all wavelengths, not just specific ones. The discrete spectrum of hydrogen was another clue that something fundamental was missing from the classical picture. The first person to make serious progress was the Danish physicist Niels Bohr. In 1913, just 2 years after Rutherford discovered the nucleus, Bohr proposed a new model of the atom. Bohr kept Rutherford's basic picture, a nucleus at the center with electrons orbiting around it, but he added a radical new rule. He postulated that electrons could only orbit the nucleus at certain specific distances, not any distance. Only particular discrete orbits were allowed. He called these allowed orbits stationary states. An electron in a stationary state, despite orbiting and therefore accelerating, did not radiate energy. This directly contradicted Maxwell's equations, and Bohr knew it. He simply declared that Maxwell's equations did not apply at atomic scales. It was a bold, almost reckless assertion, but it worked. Bohr's allowed orbits were determined by a condition involving Planck's constant, the fundamental constant of quantum physics. Max Planck had introduced this constant in 1900 while solving the black body radiation problem, and Einstein had used it in 1905 to explain the photoelectric effect. Bohr required that the angular momentum of the electron in its orbit be a whole number multiple of Planck's constant divided by 2 pi. The lowest orbit corresponded to a value of 1, the next to 2, then 3, and so on. Only these orbits were allowed, nothing in between. This immediately explained the hydrogen spectrum. When an electron jumped from a higher orbit to a lower one, it emitted a photon whose energy equaled the energy difference between the two orbits. Since only specific orbits were allowed, only specific energy differences existed, and therefore only specific wavelengths of light were emitted. Bohr calculated the predicted wavelengths, and they matched Balmer's formula and the Rydberg formula exactly. The agreement was spectacular. Bohr's model predicted hydrogen's spectral lines with extraordinary precision, and it did so by deriving them from a physical theory rather than guessing an empirical formula. But here is the crucial point for our question. In Bohr's model, the lowest allowed orbit, the ground state, had a specific, finite radius. This radius is now called the Bohr radius, and it's about 5.3 times 10 to the minus 11 meters, or roughly half an angstrom. The electron could not orbit any closer to the nucleus than this. There was no orbit below the ground state. The electron couldn't spiral inward because there was nowhere to spiral to. The lowest energy state had a definite, non-zero distance from the nucleus. The electron couldn't fall into the nucleus because the rules simply didn't allow an orbit closer than the Bohr radius. Bohr's model was a triumph in some ways and deeply unsatisfying in others. It got the right answers for hydrogen, the spectral line predictions were accurate, the atomic stability problem was solved, at least in a practical sense, but the model was held together by postulates that had no deeper justification. Why couldn't the electron orbit at any distance? Why only these specific orbits? Why did Maxwell's equations, which worked flawlessly for everything else, suddenly not apply inside atoms? Bohr had no answers. He couldn't explain why his rules worked. He just knew they did. And the model had limitations. It worked beautifully for hydrogen, which has only one electron, but for helium, which has 2 electrons, and for all heavier elements, Bohr's model gave increasingly inaccurate predictions. The model couldn't explain why some spectral lines were brighter than others. It couldn't explain the fine structure of spectral lines, the fact that when you looked very closely, some lines that appeared single were actually closely spaced pairs or triplets. It couldn't explain how atoms bonded together to form molecules. The model was a stepping stone, not a destination. What Bohr had done was recognize that something was quantized, that nature at atomic scales operated in discrete steps rather than continuous gradations. But the full explanation, the real reason why electrons don't fall into nuclei, required a much deeper revolution. A revolution that would abandon the very idea of an electron as a tiny particle following a definite path around the nucleus. A revolution that would replace the comforting, intuitive picture of an atomic solar system with something far stranger, far more abstract, and far more powerful. That revolution was quantum mechanics, and it emerged over the following decade through the work of physicists including Werner Heisenberg, Erwin Schrödinger, Max Born, Paul Dirac, Wolfgang Pauli, and others. What they discovered would overturn nearly every classical intuition about how nature works at the smallest scales. The electron doesn't orbit the nucleus. It doesn't follow a path. It doesn't have a trajectory. It doesn't exist at a definite location until you measure it. And the reason it can't fall into the nucleus isn't because some mysterious force holds it back. It's because the very concept of falling into the nucleus doesn't make sense in the framework of quantum mechanics. The rules of the game are completely different from what anyone expected. But to understand that, to really understand why the electron behaves the way it does and what it means for atomic stability, we need to enter the world of quantum mechanics properly. We need to talk about waves, probabilities, and a principle of uncertainty that sets an absolute limit on what nature allows. Because the answer to why the electron doesn't fall into the nucleus turns out to be the same answer to a much deeper question. What is matter, really, at the most fundamental level? And the answer to that question is unlike anything the classical world could have predicted. The revolution began not with atoms, but with light. And understanding how light forced physicists to rethink reality is essential to understanding why electrons behave the way they do inside atoms. Because the same strange logic that applies to light also applies to matter. And once you see that connection, the reason electrons don't collapse into the nucleus becomes not just understandable, but almost inevitable. By the late 1800s, the nature of light seemed settled. Light was a wave. This had been established through decades of careful experimentation. Thomas Young's double-slit experiment in 1803 had shown that light produces interference patterns, bright and dark bands that appear when two light waves overlap. Where the peaks of two waves align, they reinforce each other, creating bright bands. Where a peak meets a trough, they cancel, creating dark bands. Only waves do this. Particles don't produce interference patterns. If you throw baseballs through two slits in a wall, you get two piles on the other side, not an interference pattern. Light produced interference, therefore, light was a wave. Maxwell's equations confirmed this beautifully. They predicted electromagnetic waves travelling at a specific speed, and that speed matched the measured speed of light exactly. Light was an electromagnetic wave, case closed. Except it wasn't. In 1900, Max Planck was trying to solve a problem called the ultraviolet catastrophe. Classical physics predicted that a hot object should emit infinite energy at high frequencies. This was obviously wrong, because hot objects don't emit infinite energy. But the mathematics of classical wave theory insisted they should. Planck found that he could fix the problem if he assumed energy wasn't emitted continuously, but in discrete packets. He called these packets quanta. Each quantum had an energy proportional to the frequency of the light. The proportionality constant was a new fundamental number that became known as Planck's constant. Planck himself wasn't entirely comfortable with this idea. He considered it a mathematical trick, a computational device that gave the right answer without necessarily reflecting physical reality. He spent years trying to derive his result without using quanta, and failed. Then, in 1905, Albert Einstein took Planck's idea much further. Einstein was studying the photoelectric effect, a phenomenon where light hitting a metal surface ejects electrons from that surface. The puzzling thing was that whether electrons were ejected depended on the color of the light, not its brightness. Dim blue light could eject electrons from certain metals. Bright red light could not, no matter how intense. If light were purely a wave, this made no sense. A brighter light carries more energy. It should be able to eject electrons regardless of color. But Einstein proposed that light actually consists of individual particles, discrete packets of energy. Each packet, later called a photon, carries an energy determined by its frequency. Blue light has a higher frequency than red light, so each blue photon carries more energy than each red photon. If a single photon doesn't carry enough energy to knock an electron free from the metal, it doesn't matter how many photons you send, none of them individually has enough energy. 1,000 weak punches won't do what a single strong punch can. This was shocking. Light, which had been conclusively demonstrated to be a wave, was also a particle. Not one or the other, both. It behaved like a wave when it passed through slits and created interference patterns. It behaved like a particle when it hit a metal surface and ejected electrons. The same entity exhibited two completely different natures depending on how you interacted with it. This was the first crack in the classical worldview. Nature at the fundamental level was not what anyone expected. Now here is where things connect to atoms and electrons. In 1924, a French physicist named Louis de Broglie asked a question that seemed almost absurd at the time. If light, which everyone thought was a wave, also behaves as a particle, could matter, which everyone thought was particles, also behave as a wave? De Broglie proposed that every particle, every physical object, has an associated wavelength. The wavelength is inversely proportional to the particle's momentum. Heavy, fast-moving objects have extremely short wavelengths, so short that the wave behavior is completely undetectable. A baseball, a car, a human being, all have de Broglie wavelengths so incredibly tiny that no experiment could ever detect their wave nature. But for something as small and light as an electron, the wavelength becomes significant, comparable to the size of an atom. This was confirmed experimentally in 1927 by Clinton Davison and Lester Germer. They fired electrons at a nickel crystal and observed a diffraction pattern. Diffraction is something only waves do. The electrons were behaving like waves, spreading out, interfering with each other, creating patterns of high and low intensity. Individual electrons, one at a time, when fired at a crystal, eventually built up a diffraction pattern on the detector. Each individual electron landed at a specific point, like a particle. But over many electrons, the pattern of where they landed was the pattern of a wave. Electrons were both particles and waves, just like light. This wave-particle duality is not a metaphor. It's not an analogy. It's not saying electrons are like waves in some poetic sense. Electrons genuinely exhibit wave behavior. They interfere, they diffract, they have wavelengths, and this changes everything about how we understand atoms. Think about what this means for Bohr's model. Bohr said electrons could only exist in certain specific orbits around the nucleus, but he couldn't explain why. De Broglie's wave idea provided a clue. If the electron is a wave, and it's wrapped around the nucleus in a circular orbit, then the wave must connect smoothly with itself. It must form a standing wave. A standing wave is a wave that fits perfectly into a confined space, like the vibrations of a guitar string. A guitar string is fixed at both ends. It can only vibrate at certain frequencies, frequencies where a whole number of half wavelengths fit between the two fixed points. The string can vibrate with 1/2 wavelength, or 2, or 3, or 17, but it can't vibrate at 1.5 half wavelengths. That doesn't work because the wave wouldn't connect smoothly at the ends. Similarly, de Broglie proposed, the electron wave wrapping around the nucleus must fit a whole number of wavelengths into the orbit. If the circumference of the orbit equals 1 wavelength, that works. 2 wavelengths, that works. 3, 4, any whole number. But 1.5 wavelengths don't work. The wave would destructively interfere with itself. It would cancel out. Only orbits where a whole number of wavelengths fit are allowed, and this reproduced Bohr's quantization condition exactly. The whole numbers weren't arbitrary. They reflected the wave nature of the electron. But de Broglie's picture was still essentially classical in one important sense. It still imagined the electron as a wave travelling along a definite path, a circular orbit around the nucleus. The full quantum mechanical picture goes much further, and it was developed primarily by two physicists working independently, with very different mathematical approaches that turned out to be equivalent. In 1925, Werner Heisenberg developed a version of quantum mechanics based on matrices, arrays of numbers that could be manipulated mathematically to predict the outcomes of experiments. His approach was abstract and made no attempt to visualize what the electron was doing between measurements. It was purely about predicting the results of observations. In 1926, Erwin Schrödinger developed a different approach, wave mechanics, based on a mathematical object called the wave function. The wave function, usually denoted by the Greek letter psi, is a mathematical function that assigns a number, generally a complex number, to every point in space at every moment in time. Schrödinger wrote down an equation, now called the Schrödinger equation, that describes how the wave function evolves over time. This equation plays the same role in quantum mechanics that Newton's second law plays in classical mechanics. Newton's law tells you how particles move if you know the forces acting on them. Schrödinger's equation tells you how the wave function changes if you know the potential energy landscape the particle moves through. For a hydrogen atom, the potential energy comes from the electric attraction between the proton and the electron. It's negative, meaning it gets more negative as the electron gets closer to the proton. Plug this potential into Schrödinger's equation, and something remarkable happens. The equation doesn't have solutions for just any energy. Only certain specific energies are allowed. These are the energy levels of the hydrogen atom. They emerge naturally from the mathematics. You don't have to put them in by hand the way Bohr did. You don't have to postulate them. They're consequences of the equation itself, just as the allowed vibration frequencies of a guitar string are consequences of the wave equation for a vibrating string. The lowest allowed energy level, the ground state, corresponds to a specific wave function, and this wave function tells you something extraordinary about where the electron is, or more precisely, where the electron might be. The wave function itself is not directly observable. What is observable, as Max Born proposed in 1926, is the square of the wave function's magnitude. This quantity gives you the probability density. It tells you the probability of finding the electron in a particular region of space if you were to measure its position. Not where the electron is, but where it's likely to be found. The electron doesn't have a definite position until you measure it. Before measurement, it exists in a state of quantum indeterminacy, spread out across space as described by the wave function. For the ground state of hydrogen, the probability density is highest at the nucleus and falls off exponentially with distance. Wait, let that sink in. The probability density is highest at the nucleus. Does that mean the electron is most likely to be found right at the center, right at the proton? If so, hasn't the electron effectively fallen into the nucleus after all? No, and understanding why requires careful thinking about three-dimensional geometry. The probability density tells you the probability per unit volume. It's highest at the center. But when you ask where the electron is most likely to be found, you have to consider not just probability density, but also how much volume is available at each distance. Think of it this way. Imagine you're looking for the electron at a distance r from a nucleus. The set of all points at distance r from the center forms a spherical shell. The volume of that shell is proportional to r squared times the thickness of the shell. Near the nucleus, r is small, so the shell has very little volume, even though the probability density is high. Far from the nucleus, r is large, so the shell has lots of volume, but the probability density has dropped off. The most probable distance, where you're most likely to actually find the electron, is the distance where the product of probability density and shell volume is greatest. For hydrogen's ground state, this peak occurs at exactly the Bohr radius, 5.3 times 10 to the minus 11 meters. The same value Bohr calculated in 1913, but now derived from a completely different and far more fundamental theory. The electron isn't orbiting at the Bohr radius. It doesn't have a path. It doesn't trace a circle or an ellipse or any trajectory at all. It exists as a probability cloud, a fuzzy sphere of likelihood centered on the nucleus, with the most probable distance matching the Bohr radius. The cloud has no sharp edge. There's a small but non-zero probability of finding the electron very far from the nucleus, and a small but non-zero probability of finding it very close, or even, technically, inside the nucleus. But the overwhelming likelihood is that you'll find it at roughly the Bohr radius. Now we come to the heart of the matter, the reason the electron doesn't collapse into the nucleus, and the key is the Heisenberg uncertainty principle. Werner Heisenberg showed in 1927 that there are fundamental limits to how precisely certain pairs of physical properties can be known simultaneously. The most important pair for our purposes is position and momentum. The more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. This is not a limitation of measurement instruments. It's not about the clumsiness of our tools. It's a fundamental property of nature. The particle literally does not have a well-defined position and a well-defined momentum at the same time. The universe itself doesn't contain that information. The uncertainty principle is expressed mathematically as the uncertainty in position multiplied by the uncertainty in momentum being greater than or equal to Planck's constant divided by 4 pi. The product of these two uncertainties has a minimum value set by a fundamental constant of nature. You can make one uncertainty very small, but only at the cost of making the other very large. Now think about what happens if you try to confine the electron closer and closer to the nucleus. Confining the electron to a smaller region means reducing the uncertainty in its position. You're squeezing the electron into a tighter space, which means you know more precisely where it is. But the uncertainty principle says that reducing position uncertainty must increase momentum uncertainty. The electron's momentum becomes less well defined. It could be moving in any direction with a wide range of possible speeds. Higher momentum uncertainty means higher average kinetic energy. This is a direct consequence. If the momentum can take a wide range of values, including large ones, the average kinetic energy, which depends on the square of the momentum, is necessarily large. The electron might be close to the nucleus, which reduces its potential energy because of the electric attraction. But being close also means being confined, which increases its kinetic energy because of the uncertainty principle. So there are two competing effects. The electric attraction wants to pull the electron as close to the nucleus as possible, which would minimize the potential energy. The uncertainty principle says that confining the electron to a very small space increases its kinetic energy enormously. The total energy of the electron is the sum of its kinetic energy and its potential energy. The kinetic energy is always positive. The potential energy is negative, becoming more negative as the electron gets closer. As the electron gets closer to the nucleus, the potential energy decreases, which is favorable, but the kinetic energy increases, which is unfavorable. At some point, these two effects balance. There is an optimal distance where the total energy is minimized. Bringing the electron any closer would increase the kinetic energy more than it would decrease the potential energy, so the total energy would go up. Moving the electron farther away would decrease the kinetic energy less than it would increase the potential energy, so again, the total energy would go up. The minimum energy state, the ground state, occurs at this balance point. This is the ground state of the atom. It's not a state where the electron is motionless. It's not a state where the electron is at a specific distance from the nucleus. It's the quantum state of lowest possible energy, a state where the competing demands of electrical attraction and quantum confinement reach an equilibrium. The electron cannot lose any more energy because there is no lower energy state available. There is nowhere left to fall to. The ground state is the bottom, it's the floor. The electron sits there not because something is holding it up, but because down simply doesn't exist below this point. Let me say this more carefully, because it's the central answer to our question. In classical physics, the electron could have any energy. It could spiral down continuously, losing energy smoothly, getting closer and closer to the nucleus. Energy was continuous. Any value was allowed. In quantum mechanics, energy is quantized. Only specific energy values are permitted. These are the eigenvalues of the Schrödinger equation, the specific energies for which the equation has well-behaved solutions. The lowest eigenvalue is the ground state energy. It's negative, meaning the electron is bound to the nucleus. But it's not infinitely negative. It's a finite, specific value, roughly minus 13.6 electron volts for hydrogen. For the electron to get closer to the nucleus than the ground state allows, it would need to transition to a lower energy state. But there is no lower energy state. The ground state is the bottom of the ladder. There is no rung below it. The electron literally cannot fall any further because the laws of quantum mechanics don't permit a state with lower energy in which it could exist. It's not that some force is pushing the electron back outward. It's that the concept of being closer doesn't correspond to any allowed quantum state. The electron is already in the lowest possible state. There is nothing below it. This is profoundly different from classical stability. In the solar system, planets are stable because they happen to have the right velocity to maintain their orbits. If you slowed a planet down, it would spiral inward. If you sped it up, it would spiral outward. The stability is contingent, depending on conditions. In quantum mechanics, atomic stability is absolute. The ground state exists because of the mathematical structure of the Schrödinger equation combined with the uncertainty principle. No matter what you do to the atom, short of providing enough energy to remove the electron entirely or fuse the nucleus, the electron will remain in or return to the ground state. You can heat it, cool it, shake it, irradiate it. As long as the atom remains intact, the ground state persists. You can excite the electron to a higher energy level by giving it exactly the right amount of energy. A photon with the right frequency can bump the electron from the ground state to the second level, or the third, or higher. But the electron won't stay there. It will spontaneously emit a photon and drop back down, eventually returning to the ground state. The ground state is the natural resting place, the default configuration, the bottom. This also explains why atoms emit light at specific wavelengths. The energy levels are discrete. When an electron drops from one level to another, it emits a photon whose energy equals the difference between the two levels. Since only specific energy differences are possible, only specific photon energies are emitted. Specific energies mean specific frequencies, which means specific wavelengths. The spectral lines that Balmer and Rydberg catalogued, that Bohr explained with his postulated orbits, emerge naturally and inevitably from Schrödinger's equation. They're not put in by hand. They're consequences of the mathematics. Let me address something that often causes confusion. When people hear that the electron is described by a wave function, a probability cloud, they sometimes imagine that the electron is really a tiny particle somewhere inside that cloud, and we just don't know exactly where. This is a natural thing to think, but it's wrong. The electron is not a tiny ball hiding somewhere in the cloud. The cloud is the electron. The wave function is the complete description of the electron's state. There is no additional information about where the electron really is. Before measurement, the electron genuinely doesn't have a definite position. It's not that we're ignorant of its position, it's that position as a concept simply isn't well defined for the electron, until a measurement forces it to take a definite value. This is one of the most counterintuitive aspects of quantum mechanics. We are used to objects having definite properties, whether we look at them or not. A ball is somewhere, even when no one is watching. But quantum mechanics says this isn't true for electrons, photons, and all other quantum objects. Their properties are indeterminate until measured. The act of measurement doesn't reveal a pre-existing value, it creates the value. Before you measure the electron's position, the electron doesn't have a position. It has a wave function that gives probabilities for various positions. Measurement collapses the wave function to a specific value. Einstein famously objected to this interpretation. He felt that quantum mechanics must be incomplete, that there must be hidden variables, additional information we don't yet know, that would restore determinism and give particles definite properties at all times. He expressed this discomfort with his famous remark about whether the moon exists when no one is looking at it. But decades of experiments, culminating in the Bell test experiments beginning in the early 1970s and continuing to the present day, have shown conclusively that no hidden variable theory can reproduce all the predictions of quantum mechanics while maintaining certain reasonable assumptions about locality. Quantum indeterminacy appears to be genuine. It's not a gap in our knowledge, it's a feature of reality. This matters for atomic stability because it means the electron's behavior in an atom is fundamentally different from anything in classical physics. The electron is not a tiny ball orbiting the nucleus that somehow avoids falling in. It's a quantum entity described by a wave function spread across space in a probability cloud, existing in a quantized energy state that has a natural minimum. The minimum arises because the laws of quantum mechanics, encoded in the Schrödinger equation and the uncertainty principle, demand it. There's another way to see why the ground state must have non-zero energy and non-zero spatial extent. Consider what would happen if the electron were right at the nucleus with zero spatial extent. The position uncertainty would be essentially zero because you'd know exactly where the electron is, right at the center. The uncertainty principle then demands that the momentum uncertainty be infinite. Infinite momentum uncertainty means the kinetic energy would be infinite. The total energy would be infinitely large and positive, not the negative bound state we need. So a perfectly localized electron at the nucleus isn't a low energy state at all, it's an infinitely high energy state. The atom spontaneously avoids this because nature always seeks the lowest available energy state. The ground state wave function of hydrogen is actually quite simple mathematically. It's a spherically symmetric function that decreases exponentially with distance from the nucleus. It has no angular dependence. It looks the same in every direction. This is the shape that minimizes the total energy given the constraints imposed by quantum mechanics. It's the optimal compromise between getting close to the nucleus to minimize potential energy and spreading out enough to keep kinetic energy under control. Higher energy states have more complex shapes. The second energy level includes states with angular dependence, wave functions shaped like dumbbells or rings rather than simple spheres. These correspond to the familiar s, p, d, and f orbitals of chemistry. Each shape represents a different way the wave function can arrange itself, a different standing wave pattern in 3 dimensions around the nucleus. Higher energy levels have more nodes, points or surfaces where the wave function crosses zero, just as higher harmonics on a guitar string have more nodes along the string. The quantum numbers that label these states, the principal quantum number, the angular momentum quantum number, the magnetic quantum number, these are not arbitrary labels. They emerge from the mathematics of the Schrödinger equation applied to the Coulomb potential of the nucleus. They specify the energy, the shape, and the orientation of each allowed state. They tell you how many nodes the wave function has, how it behaves under rotation, how it responds to external magnetic fields. The entire structure of the periodic table, all of chemistry, all of molecular biology, all of material science, emerges from these quantum numbers and the wave functions they describe. Bohr was right that something was quantized, but what he didn't understand was the reason. The quantization doesn't come from a rule imposed on orbits. It comes from the wave nature of matter, combined with boundary conditions. Just as a violin string can only vibrate at frequencies where standing waves fit between the two fixed ends, the electron wave function in an atom can only take forms that are well behaved everywhere in space, finite at the nucleus and falling to zero at infinity. Only certain energies permit such solutions. The quantization is as natural and inevitable as the notes of a musical instrument. It's a consequence of waves in a confined system, and the ground state, the lowest note, the fundamental frequency, has a non-zero energy and a non-zero spatial extent. The electron doesn't fall into the nucleus because the laws of quantum mechanics don't allow a state with lower energy than the ground state. The atom is stable not because of some force pushing the electron outward, not because of some balance of orbital motion and electrical attraction in the classical sense, but because the quantum structure of reality has a flaw. There is a lowest state. The electron is already in it, and there is simply nowhere further down to go. This is one of the most beautiful and profound results in all of science. The stability of every atom in the universe, the reason matter exists, the reason chemistry works, the reason you are here, all of it traces back to the wave nature of matter and the uncertainty principle. These quantum mechanical effects, discovered barely a century ago, are responsible for the existence of everything you have ever seen, touched, or experienced. Without them, atoms would collapse in a billionth of a second, and the universe would be nothing but radiation and bare nuclei. Quantum mechanics isn't just an abstract theory about tiny particles. It's the reason there is a world at all. So we now understand why the electron doesn't fall into the nucleus. Quantum mechanics forbids it. The wave nature of matter, the uncertainty principle, the quantized energy levels of the Schrödinger equation, all of these conspire to create a ground state with finite energy and finite spatial extent. The electron can't fall any further because there's no quantum state below the ground state. The floor exists, and the electron is already standing on it. But we've been talking about what the electron does without really addressing what the electron is. We've described its behavior inside atoms. We've talked about wave functions and probability clouds and energy levels. But none of that tells us what this thing actually is at the most fundamental level. What is an electron made of? Does it have parts? Does it have a size? Does it have a shape? Is it a tiny ball of something? A knot in some fabric? A vibration in some field? Or is it something so unlike anything in ordinary experience that these questions don't even have meaningful answers? These are not philosophical questions. They're physics questions. And physics has answers, though the answers are strange. Let's start with what we know from experiment. The electron has three intrinsic properties that define it. It has a mass of about 9.11 times 10 to the minus 31 kilograms. That's extraordinarily small. A single grain of sand contains roughly 50 billion trillion electrons. Each one has this tiny mass. The electron also has an electric charge of minus 1.6 times 10 to the minus 19 coulombs. This is the fundamental unit of electric charge. Every electric charge ever measured in nature is a whole number multiple of this value. Protons have exactly the same magnitude of charge, but positive. Nobody knows why the electron and proton charges are exactly equal in magnitude. It's one of the unexplained features of the Standard Model. And the electron has a property called spin, with a value of 1/2 in units of Planck's constant divided by 2 pi. Now, spin is one of those things that sounds familiar, but is deeply misleading. When physicists say the electron has spin, it's natural to imagine it's rotating, spinning on its axis like a tiny top, or like the Earth spinning once every 24 hours. But that's not what spin means in quantum mechanics. Spin is an intrinsic angular momentum that has no classical analogue. The electron isn't actually rotating. Nothing inside the electron is moving in circles. Spin is a purely quantum mechanical property that particles simply have, the same way they have mass and charge. It doesn't correspond to any physical rotation. Here's one way to see why spin can't be ordinary rotation. The electron, as far as any experiment has ever determined, has no measurable size. It's a point particle. If it were spinning, the surface, if it had a surface, would need to be moving. But for a point particle, there is no surface. There's no extent to rotate. Even if you gave the electron a tiny hypothetical radius, you could calculate how fast its surface would need to spin to produce the observed angular momentum. The answer comes out faster than the speed of light, often many times faster. That's physically impossible. Nothing can move faster than light. So the electron's spin is definitely not the result of physical rotation. It's something else entirely, a quantum property with no classical counterpart, built into the fabric of reality at the most fundamental level. Spin has measurable consequences though. When you place an electron in a magnetic field, it behaves as though it were a tiny magnet. It has a magnetic moment. This magnetic moment interacts with external magnetic fields, causing energy level splitting, which is observed in experiments. This was first seen in the Stern-Gerlach experiment of 1922, before the concept of spin was even fully understood. Otto Stern and Walther Gerlach sent a beam of silver atoms through an inhomogeneous magnetic field and found the beam split into two distinct components, not a continuous smearing, but two sharp lines. This implied the magnetic moment, and therefore the angular momentum, could only take two discrete values. For an electron, those two values correspond to spin up and spin down, two options, nothing in between. Quantized, like everything else at this scale. So the electron has mass, charge, and spin. These are its defining properties, but what is it made of? Here's the answer from modern physics, and it might be frustrating at first. As far as we know, the electron isn't made of anything. It has no internal structure, no components, no parts. It's not built from smaller pieces the way a proton is built from quarks, or a nucleus is built from protons and neutrons, or an atom is built from a nucleus and electrons. The electron is fundamental. It's one of the basic building blocks that don't break down into anything simpler. But saying the electron has no internal structure isn't a guess or an assumption. It's a conclusion based on extensive experimental evidence, and understanding the evidence requires talking about how physicists probe the structure of very small things. The basic method is scattering. You take a beam of particles, accelerate them to high energy, and slam them into the object you want to study. Then you look at how the beam particles bounce off, scatter, and from the pattern of scattering, you deduce the structure of the target. This is essentially what Rutherford did with alpha particles and gold foil. The scattering pattern told him the atom's positive charge was concentrated in a tiny nucleus, rather than spread throughout the atomic volume. The same technique was applied to the proton, starting in the late 1960s at the Stanford Linear Accelerator Center, known as SLAC. Physicists fired high-energy electrons at protons and measured how the electrons scattered. If the proton were a featureless point, the scattering pattern would follow a specific mathematical form. If the proton had internal structure, if it contained smaller objects inside it, the pattern would deviate from the point particle prediction in specific, calculable ways. The experiments, led by Jerome Friedman, Henry Kendall, and Richard Taylor, found dramatic deviations. The electrons were bouncing off hard, point-like objects inside the proton. The scattering pattern was exactly what you'd expect if the proton contained three small, nearly point-like constituents. These constituents were initially called partons, a name coined by Richard Feynman. They were later identified as quarks, the particles theorized independently by Murray Gell-Mann and George Zweig in 1964. The deep inelastic scattering experiments proved that protons are composite objects. They have internal structure. They're made of smaller things. Now here's the critical point. The same type of experiment has been performed on the electron itself. Physicists have collided electrons with other electrons, with positrons, with photons, at the highest energies available at particle accelerators around the world. They've looked for any sign that the electron has internal structure, any deviation from point particle behavior, any hint that it might contain smaller constituents, and they found nothing. Absolutely nothing. The experiments at the Large Electron-Positron Collider at CERN, which operated from 1989 to 2000, probed the electron structure down to distances of about 10 to the minus 18 meters. That's a billionth of a meter, 1,000 times smaller than a proton. And at that scale, the electron still behaves like a perfect point particle. No structure, no subcomponents, no hint of anything inside. More recent experiments at other facilities have pushed even further, and the conclusion remains the same. Down to the smallest distances we can currently probe, the electron has no size and no internal structure. This doesn't mean the electron is literally a mathematical point with zero size in every possible theory. It means that in every experiment we've been able to conduct, the electron behaves indistinguishably from a point particle. Whatever the electron is, it's smaller than anything we can currently measure. And in the standard model of particle physics, the theoretical framework that describes all known particles and forces, the electron is treated as a fundamental, elementary, structureless point particle. It's not made of anything else. It is itself the fundamental thing. This puts the electron in a special category. Protons have structure. They're made of 2 up quarks and 1 down quark bound together by gluons, the carriers of the strong nuclear force. Neutrons similarly contain 1 up quark and 2 down quarks plus gluons. Atoms have structure. Molecules have structure. But electrons, as far as we can tell, do not. They are among the truly elementary particles of nature, alongside quarks, neutrinos, and a few others. The standard model of particle physics classifies all known fundamental particles into 2 groups: fermions, which are the matter particles, and bosons, which are the force-carrying particles. Fermions include quarks, which come in 6 flavors: up, down, charm, strange, top, and bottom, and leptons, which also come in 6 types: the electron, the muon, the tau, and 3 corresponding neutrinos. The electron is the lightest charged lepton. The muon is essentially a heavier copy of the electron, about 207 times more massive, but otherwise identical in its interactions. The tau is heavier still, about 3,477 times the electron's mass. Why 3 copies exist, why nature repeats the same pattern at 3 different mass scales, is one of the great unsolved puzzles in physics. Nobody knows why there are exactly 3 generations of leptons and quarks. The standard model describes this fact, but doesn't explain it. So the electron is a fundamental lepton with no known internal structure. But saying it's a point particle raises a conceptual problem. If the electron is literally a point, a mathematical zero-dimensional object with no extent whatsoever, then its charge density is infinite at that point. All of its charge is concentrated in 0 volume, and when you try to calculate the energy stored in the electric field of a point charge, you get infinity. The electric field gets stronger and stronger as you approach the point, and the energy in the field grows without bound. Classically, a point charge has infinite self-energy. This is a problem that plagued physics for decades. Quantum field theory resolves this problem, but in a way that requires some explanation. Because quantum field theory is where the deepest modern understanding of what an electron actually is resides, and that understanding is radically different from any picture you might have in your head. In quantum field theory, the fundamental entities are not particles, they are fields. A field is a physical quantity that has a value at every point in space and every moment in time. You're already familiar with some fields from classical physics. The temperature at every point in a room is a field. The air pressure at every point in the atmosphere is a field. The electric and magnetic fields that Maxwell described are fields. In quantum field theory, there is a field for every type of fundamental particle. There is an electron field that permeates all of space-time. There is an up quark field, a down quark field, an electromagnetic field, a Higgs field, and so on. Each field fills the entire universe, everywhere, all the time. What we call a particle is an excitation of the corresponding field. An electron is not a tiny ball sitting in space. An electron is a localized excitation, a vibration, a ripple in the electron field. Think of a calm lake. The water extends everywhere, smooth and featureless. Now drop a pebble. A ripple appears. That ripple is localized. It has a position, it moves, it carries energy and momentum. But it's not a separate object floating on the water. It is the water. It's a disturbance in the water, an excitation of the underlying medium. The electron is like that ripple, except the medium isn't water. It's the electron field, a quantum field that permeates all of space-time. When we say we've created an electron, what we really mean in the language of quantum field theory is that we've excited the electron field. We've added a quantum of energy to the field in a localized region, and that quantum manifests as what we observe and measure as a particle. When an electron is destroyed, say by annihilating with a positron, the excitation disappears. The energy goes into exciting other fields, typically the electromagnetic field, producing photons. Fields get excited and de-excited. Energy flows from one field to another, and the localized excitations of these fields are what we call particles. This is a profound shift in perspective. In the classical view, particles are the primary things. They exist as definite objects at definite locations with definite properties. Fields are secondary, generated by particles. Electric fields are created by charges. Gravitational fields are created by masses. The particles come first, and the fields are consequences. In quantum field theory, the hierarchy is reversed. The fields are primary. They are the fundamental entities. They exist everywhere, at all times. Particles are secondary. They are excitations of the fields, temporary disturbances in the underlying quantum medium. Every electron in the universe is an excitation of the same electron field. Your electrons and my electrons are ripples in the same field. This is why all electrons are identical. In classical physics, if electrons were little balls, you'd have to explain why every single one has exactly the same mass, exactly the same charge, exactly the same spin. How can billions of trillions of separate objects be so precisely identical? It would be like finding that every grain of sand on every beach on Earth was exactly the same size, same shape, same weight, down to the last atom. In classical physics, this would be a baffling coincidence. In quantum field theory, it's trivially explained. All electrons are identical because they're all excitations of the same field. They have the same properties because the field has those properties. Asking why all electrons have the same charge is like asking why all ripples in a lake are made of water. They're excitations of the same underlying entity. Of course they're identical. The quantum field theoretic picture also provides a deeper understanding of what happens when we say the electron has no internal structure. A truly composite particle, one made of smaller parts, would be an excitation of multiple fields bound together. A proton is an excitation involving the up quark field, the down quark field, and the gluon field, all interacting with each other in a complicated bound state. The internal structure of the proton reflects the fact that it's a composite excitation involving several different fields. The electron, by contrast, appears to be a simple excitation of a single field, the electron field. There's no evidence that it involves multiple fields or multiple excitations bound together. It's as simple as an excitation can be. One field, one quantum, one particle. Now there's a subtlety here that's important. When we say the electron is a point particle, we mean that the electron field's excitation, when probed at high energies, behaves as though it has no spatial extent. But quantum field theory also tells us that the electron is never truly alone. The electron interacts with other fields, most importantly, the electromagnetic field. And these interactions change how the electron appears at different scales. Consider a bare electron, a hypothetical electron with no interactions. This bare electron would have some intrinsic mass and charge. But real electrons interact with the electromagnetic field, and this interaction changes everything. The electron constantly emits and reabsorbs virtual photons. These photons, in turn, can briefly create virtual electron-positron pairs from the vacuum. Those pairs can emit and absorb their own virtual photons. The result is a seething cloud of virtual activity surrounding every electron at all times. I should be careful about what virtual particles means here. Virtual particles are not particles in the ordinary sense. They're not things you could detect with a particle detector. They're mathematical terms that appear in the perturbative calculations of quantum field theory, representing quantum fluctuations in the fields. When physicists draw Feynman diagrams showing an electron emitting and reabsorbing a virtual photon, they're not depicting a literal sequence of events you could observe. They're representing a term in a mathematical expansion, a contribution to the probability amplitude for some process. The virtual particles are a computational tool, a way of organizing the mathematics of quantum field theory into manageable pieces. But the effects of these quantum fluctuations are real and measurable. One of the most dramatic effects is on the electron's magnetic moment. Remember, the electron behaves like a tiny magnet due to its spin. The strength of this magnetic moment is characterized by a quantity called the g-factor. In simple quantum mechanics, Dirac's equation predicts the electron's g-factor should be exactly 2. But when you include the effects of virtual photons and virtual particle-antiparticle pairs from quantum electrodynamics, the g-factor shifts slightly away from 2. The deviation is called the anomalous magnetic moment. This is one of the most precisely tested predictions in all of science. The theoretical prediction, calculated to 10th order in the perturbation expansion using quantum electrodynamics, gives a value for the electron's anomalous magnetic moment of approximately 0.001159652181228. The experimental measurement, using exquisitely sensitive devices called penning traps that can hold a single electron in isolation for months while measuring its magnetic properties, gives a value of approximately 0.001159652181073. These numbers agree to better than 1 part in a billion. The theoretical value and the measured value match to roughly 10 significant figures. There is no other prediction in any field of science that has been verified to this level of precision. Think about what this means. The quantum field theory picture of the electron, treating it as an excitation of a quantum field, constantly interacting with virtual photons and virtual pairs, predict the electron's magnetic properties to an accuracy of 1 part in 10 billion. This isn't a rough estimate. This isn't an order of magnitude calculation. This is a prediction accurate to the 10th decimal place, confirmed by experiment. If your theory of what the electron is gives you this level of agreement with reality, you're probably doing something right. This extraordinary agreement also tells us something important about the electron's structure, or rather, its lack of structure. If the electron were composite, if it were made of smaller parts bound together, those parts would affect the magnetic moment in ways that would show up as discrepancies between the quantum electrodynamics prediction and the measured value. The fact that the prediction matches so precisely, with no unexplained discrepancies, places extremely tight constraints on any possible substructure. If the electron has parts, those parts must be so tightly bound and so far beyond our current energy reach that they leave no detectable signature even at the level of precision where we can measure 1 part in 10 billion. Now, could the electron be composite despite all this evidence? Could it be made of smaller things that we simply can't see yet? In principle, yes. Physics is an empirical science, and we can only know what our experiments tell us. The history of physics is full of examples where something thought to be fundamental turned out to be composite. Atoms were once thought to be indivisible. Then we found they contain electrons and nuclei. Nuclei were once thought to be fundamental. Then we found they contain protons and neutrons. Protons and neutrons were once thought to be fundamental. Then we found they contain quarks. At each level, higher energy experiments revealed deeper structure. Could the same thing happen to the electron? There are theoretical models that propose exactly this. Preon models, developed in the 1970s and 80s by physicists including Yogesh Patti, Abdus Salam, Haim Harari, and Michael Shoup, propose that quarks and leptons, including the electron, are made of smaller constituents called preons. Different preon models use different names and different structures, but the basic idea is the same. The particles we think of as fundamental are actually composite, made of a smaller set of truly fundamental building blocks. Preon models are attractive because they could explain some features of the standard model that currently have no explanation. Why are there exactly 3 generations of quarks and leptons? Maybe different generations correspond to different combinations or excitations of preons. Why do quarks and leptons have the charges they do? Maybe those charges arise from the charges of their constituent preons, the way a proton's charge arises from the charges of its constituent quarks. Why are there specific relationships between certain particle properties? Maybe those relationships reflect the underlying preon structure. But preon models face severe experimental constraints. If electrons were composite, you'd expect to see evidence at some energy scale. Excited states of the electron, analogous to excited states of the proton. Deviations from point particle scattering at high energies. Anomalies in precision measurements like the G factor. None of these have been observed. The experimental limits on electron substructure push any possible compositeness scale to extremely high energies, far beyond what current accelerators can reach. The constraints from the electron's anomalous magnetic moment alone are devastating. Any preon model must explain why its predictions are indistinguishable from those of a point-like electron to 1 part in 10 billion. That's a very hard requirement to meet. There are also theoretical challenges. If the electron is made of preons, what holds the preons together? A new force, stronger than anything we've observed. But a force that strong should produce effects we'd notice at lower energies. The binding energy would contribute to the electron's mass, but the electron's mass is tiny compared to the energy scales where compositeness might appear. This is a fine-tuning problem, similar to ones that plague other areas of physics. Most physicists today regard preon models as disfavored, but not completely ruled out. The electron might have structure at scales far beyond our current experimental reach. But as of now, every piece of evidence points to the electron being fundamental. A structureless, point-like excitation of the electron field, not made of anything else, not decomposable into smaller parts, simply itself. This raises a philosophical question that physics doesn't fully answer. If the electron isn't made of anything, if it has no parts, no internal structure, what gives it its properties? Why does it have the mass it does? Why does it have the charge it does? Why spin 1/2 rather than 0 or 1 or 3/2? In the standard model, these values are parameters. They're measured experimentally and plugged into the theory. The theory doesn't predict them. It doesn't explain why the electron's mass is 9.11 times 10 to the minus 31 kilograms rather than some other value. It simply says, this is the mass, we measured it, and here is how the theory uses it. The Higgs mechanism, confirmed by the discovery of the Higgs boson at the Large Hadron Collider in 2012, explains how particles acquire mass. Before electroweak symmetry breaking, all the fundamental particles in the standard model are massless. The Higgs field, which has a non-zero value everywhere in space, interacts with particles and gives them mass. Different particles interact with the Higgs field with different strengths, and this determines their masses. The electron interacts weakly with the Higgs field, which is why it's light. The top quark interacts strongly, which is why it's heavy, roughly 340,000 times more massive than the electron. But the Higgs mechanism doesn't explain why the strengths of these interactions are what they are. It explains how particles get mass, the mechanism by which mass arises, but it doesn't explain why each particle gets the specific mass it does. The coupling strengths between particles and the Higgs field are free parameters of the standard model, measured but not predicted. Why the electron has its particular mass remains unexplained. The standard model contains about 19 free parameters, numbers that must be determined by experiment rather than derived from first principles. The electron mass is one of them. The charge is related to another, the electromagnetic coupling constant. These are inputs to the theory, not outputs. Could a deeper theory explain these values? Many physicists believe so. String theory, for example, might in principle predict particle masses and charges from the geometry of extra dimensions. If the extra dimensions have a specific shape, a specific topology and size, the vibrations of strings in that geometry would correspond to specific particles with specific properties. The electron's mass might be determined by the geometry of space-time at scales far smaller than we can currently probe. But we don't know which geometry is the right one, and the number of possibilities is enormously large, perhaps 10 to the 500 or more. Without knowing the geometry, we can't make predictions. This is one of the major open problems in theoretical physics. So what is an electron actually made of? The honest answer from modern physics is this. The electron is a fundamental excitation of the electron field, a quantum field that pervades all of space-time. It has mass, electric charge and spin, but no known internal structure, no components, no parts. It is not made of anything smaller as far as any experiment has ever been able to determine. Its properties are described with extraordinary precision by quantum electrodynamics, but the ultimate origin of those properties, why the electron has the mass and charge it does, remains one of the deepest open questions in physics. The electron is elementary. It is itself the fundamental entity, and everything you've ever seen, every atom, every molecule, every star, every galaxy, is built from objects like it, fundamental quantum field excitations, whose basic nature remains, in some ultimate sense, mysterious. We've now arrived at a picture of the electron that's radically different from anything you might have imagined before starting this journey. The electron is not a tiny ball, it's not a speck of charged matter. It's a fundamental excitation of a quantum field, a ripple in an invisible medium that fills the entire universe. It has no known internal structure. It has no known size. And the reason it doesn't fall into the nucleus has nothing to do with speed, or orbits, or centrifugal force. It has to do with the quantum structure of reality itself. The fact that energy levels are quantized, and the ground state has a floor that cannot be crossed. But there's still more to the story. Because the electron, even though it's fundamental, even though it appears to be structureless, is far more complicated than it first seems. The reason has to do with the quantum vacuum and the way the electron interacts with the fields around it. When you look closely enough, the electron is never truly alone. It exists in a constant state of interaction with the electromagnetic field and with the other quantum fields of nature. And these interactions affect what the electron looks like, how it behaves, and even what we mean when we talk about its properties. To understand this, we need to go deeper into quantum electrodynamics, the theory known as QED. This is the quantum field theory of electrons, positrons, and photons. It describes how electrically charged particles interact with each other through the exchange of photons, and it is, by any measure, the most precisely tested theory in the history of science. We touched on its predictions for the electron's magnetic moment a moment ago, but QED contains much more than that single prediction. It provides a complete framework for understanding the electron's interactions, and in doing so, it reveals something surprising about the nature of the electron's charge and mass. In classical electromagnetism, the electron has a definite charge of -1.6 times 10 to the -19 coulombs. That's a fixed number. It doesn't change. It doesn't depend on how you look at the electron or from what distance you observe it. But in QED, things are different. The charge you measure depends on the energy scale at which you probe the electron, and the reason for this is a phenomenon called vacuum polarization. Here is what happens. The electron sits in the quantum vacuum, but the quantum vacuum is not empty. It's the lowest energy state of all the quantum fields, and that state is not nothingness. It's a seething sea of quantum fluctuations. The electromagnetic field fluctuates, the electron field fluctuates, all the fields fluctuate, constantly, everywhere, all the time. These fluctuations are a direct consequence of the uncertainty principle applied to quantum fields. Just as you can't simultaneously know the exact position and momentum of a particle, you can't simultaneously know the exact value of a field and its rate of change at every point. The fields must fluctuate. One consequence of these fluctuations is that the vacuum around the electron is not passive. The electron's electric field affects the vacuum, and the vacuum responds. The electron's electric field can temporarily create virtual electron-positron pairs from the quantum fluctuations. A virtual positron, being positively charged, is attracted toward the real electron. A virtual electron, being negatively charged, is repelled away. So the virtual pairs become polarized, oriented with their positive ends toward the real electron and their negative ends away. This is vacuum polarization. The vacuum around the electron becomes a dielectric medium, a screen of virtual charge that partially cancels the real electron's charge. If you probe the electron from far away, at low energies, you see a charge that's partially screened by this cloud of virtual pairs. The effective charge is smaller than the bare charge. This screened charge is what we measure in everyday experiments. It's the familiar value of 1.6 times 10 to the -19 coulombs. But if you probe the electron at very high energies, which means very short distances, you penetrate deeper into the virtual cloud. You get closer to the bare electron, and you see a larger effective charge because less screening is between you and the real charge. This means the electron's charge runs with energy scale. At low energies, the charge is smaller. At high energies, the charge is larger. The electromagnetic coupling constant, which measures the strength of the electromagnetic force, increases as you go to higher energies. This is a prediction of QED, and it has been confirmed experimentally. Measurements at different energies show exactly the running predicted by the theory. This running of the coupling constant has profound implications. It means that what we call the charge of the electron isn't a single fixed number. It's a function of the energy scale at which you measure it. The charge we quote in textbooks, the familiar value, is the low energy limit, the value measured at the energy scales of everyday life. At higher energies, the charge is different. The electron's properties aren't static. They depend on how closely you look. Something similar happens with the electron's mass. In QED, the electron interacts with the electromagnetic field, emitting and reabsorbing virtual photons. These interactions contribute to the electron's energy, and since energy and mass are equivalent through Einstein's equation, they contribute to the electron's mass. The bare mass of the electron, its mass in the hypothetical absence of all interactions, is different from the observed mass. The observed mass includes contributions from the electromagnetic self-energy, the energy stored in the electron's interaction with its own field. In classical electromagnetism, calculating the self-energy of a point charge gives infinity. The energy stored in the electric field diverges as you approach the charge. In QED, the same infinity appears in the quantum calculations. When you compute the electron's self-energy using Feynman diagrams, you get integrals that diverge. The answer is infinity, which is obviously wrong because the electron has a finite, measured mass. This is where renormalization enters the story. Renormalization is a mathematical procedure developed in the late 1940s by Richard Feynman, Julian Schwinger, Sin Itiro Tomonaga, and Freeman Dyson. The basic idea is this. The infinities that appear in QED calculations are always of a specific form. They can be absorbed into redefinitions of the electron's mass and charge. Instead of using the bare mass and bare charge in your equations, you replace them with the observed physical mass and charge. The infinities get absorbed into the difference between the bare and physical values. Once you've done this, all remaining calculations give finite, well-defined answers. This sounds like a trick, and initially many physicists were skeptical. You have infinities, and you hide them by redefining your parameters. Is that legitimate? Feynman himself expressed discomfort with renormalization, calling it a shell game. But there's a deeper justification. Renormalization isn't just about hiding infinities, it reflects a genuine physical insight. We never observe the bare electron. We always observe the dressed electron, the physical electron surrounded by its cloud of virtual particles and field interactions. The bare parameters are unobservable. They're artifacts of the mathematical formalism. The physical renormalized parameters are what we actually measure, and the theory, expressed in terms of physical parameters, gives finite predictions that agree with experiment to extraordinary precision. The success of renormalization in QED is not just qualitative, it's quantitative. After renormalization, QED predictions match experiments to roughly 10 significant figures in the case of the electron's anomalous magnetic moment. This level of agreement is unmatched anywhere else in science. It tells us that QED, despite the infinities that appear in intermediate steps of calculation, correctly captures the physics of electrons and photons at the deepest level we can currently test. But renormalization also teaches us something about the nature of physical quantities. The mass and charge of the electron aren't intrinsic, bare properties of some naked point particle. They're effective quantities that emerge from the interaction of the bare excitation with the quantum vacuum. The electron you observe in an experiment isn't a bare electron. It's a bare electron plus a cloud of virtual photons, plus virtual electron-positron pairs, plus virtual muon-antimuon pairs, plus virtual quark-antiquark pairs, plus contributions from every other charged field in nature. The observed mass and charge include all of these contributions. They're collective properties of the electron plus vacuum system, not properties of an isolated point. This gives the electron a kind of structure, even though it's a fundamental particle. Not structure in the sense of being made of smaller parts, but structure in the sense of having a complex interaction with the vacuum that affects its apparent properties at different scales. At very large distances, you see the fully dressed electron with its screened charge. At shorter distances, you see through more of the screening and perceive a stronger charge. At different energy scales, the effective mass shifts slightly as different virtual processes become important. The electron is fundamental, but it's dressed in a coat of virtual interactions that changes depending on how closely you look. This connects to a broader principle in modern physics called the renormalization group, developed by Kenneth Wilson in the 1970s. Wilson showed that the behavior of physical systems at different scales is connected by a mathematical framework that describes how effective parameters change as you zoom in or out. At each scale, you can describe the physics using effective parameters appropriate for that scale. As you zoom in, the parameters change, flowing according to specific equations. The renormalization group isn't specific to QED. It applies to all of physics, from condensed matter systems to particle physics. It provides a unified way of thinking about how physics at different scales connects, how the large emerges from the small, and how the properties we measure at one scale relate to the more fundamental physics at smaller scales. Wilson's work earned him the Nobel Prize in 1982, and it transformed how physicists think about quantum field theory. Before Wilson, renormalization was a procedure, a recipe for removing infinities. After Wilson, renormalization was understood as a deep principle about the scale dependence of physical descriptions. Every theory is an effective theory, valid at some range of scales. At smaller scales, new physics might appear. The Standard Model itself is probably an effective theory, a description that works brilliantly at the energy scales we can currently probe, but might break down at much higher energies, when new particles, new forces, or new principles take over. This brings us to one of the most intriguing aspects of the running coupling constants. In the Standard Model, there are three fundamental forces described by quantum field theories: the electromagnetic force, the weak nuclear force, and the strong nuclear force. Each has its own coupling constant, measuring its strength, and each coupling constant runs with energy scale. The electromagnetic coupling gets stronger at higher energies. The strong force coupling gets weaker at higher energies, a property called asymptotic freedom, discovered by David Gross, David Politzer, and Frank Wilczek in 1973, which won them the Nobel Prize. The weak force coupling has its own behavior. What's remarkable is that when you extrapolate the three coupling constants to very high energies, they appear to converge. They nearly meet at a single point, at an energy scale of roughly 10 to the 15 to 10 to the 16 giga-electron volts, which corresponds to a distance scale of roughly 10 to the minus 31 to 10 to the minus 32 meters. This is many orders of magnitude beyond what any current or foreseeable accelerator can reach. But the approximate convergence of the coupling constants is tantalizing. It suggests that at very high energies, all three forces might unify into a single force, described by a single coupling constant. This is the idea behind grand unified theories. Grand unified theories propose that the electromagnetic, weak, and strong forces are all different aspects of a single unified force that existed in the very early universe when energies were extremely high. As the universe cooled after the Big Bang, symmetry breaking occurred, and the single force split into the three separate forces we observe today. In a grand unified theory, the electron and the quarks would be related. They'd be different states of the same underlying field, connected by symmetry transformations. The fact that the electron's charge is exactly equal in magnitude to the proton's charge, which is otherwise a complete mystery in the Standard Model, would be explained by the unifying symmetry. Grand unified theories make predictions. The most dramatic is proton decay. If quarks and leptons are unified, then there should be processes that transform quarks into leptons, meaning protons could decay. The predicted lifetime is extremely long, roughly 10 to the 34 years or more, far longer than the age of the universe. But if you watch enough protons for long enough, you should occasionally see one decay. Experiments like Super Kamiokande in Japan have been watching enormous tanks of ultra-pure water for decades, looking for proton decay. So far, none has been observed, which rules out certain grand unified models and constrains others. But more sophisticated versions of grand unification remain viable. Even grand unified theories leave questions unanswered. Why do 3 generations exist? Why does the electron have its particular mass? Why is gravity so much weaker than the other forces? These questions push us toward even more ambitious theoretical frameworks. String theory, loop quantum gravity, and other approaches to quantum gravity attempt to address some of these issues, but none has yet produced testable predictions that can be verified with current technology. Let me pull back from the frontier of theoretical physics and return to the questions we started with. What is an electron made of, and why doesn't it fall into the nucleus? We now have answers to both, and the answers are connected in a deep and beautiful way. The electron is a fundamental excitation of the electron field, a quantum field that pervades all of space-time. It has mass, charge, and spin, but no internal structure. Its observed properties are not bare intrinsic values, but addressed by interactions with the quantum vacuum, shaped by virtual photons and virtual particle pairs that surround it at all times. The dressed electron, the one we measure in experiments, is an irreducibly quantum object whose properties run with energy scale, changing depending on how closely you look. The electron doesn't fall into the nucleus because the quantum mechanical structure of the atom forbids it. The wave nature of the electron, described by the Schrödinger equation, means the electron doesn't have a definite trajectory. It doesn't orbit the nucleus like a planet. It exists as a wave function spread across space, a probability cloud whose shape is determined by the allowed quantum states. The uncertainty principle creates a fundamental tension between confining the electron near the nucleus and the kinetic energy cost of that confinement. The ground state, the lowest possible energy state, represents the optimal balance between these competing effects. Below the ground state, there is no allowed quantum state. The electron cannot fall further because there is nowhere further to fall. These two answers, what the electron is and why it doesn't collapse, are unified by quantum mechanics. The same framework that tells us the electron is a field excitation also tells us why atoms are stable. The same uncertainty principle that makes the electron's position fundamentally indeterminate also prevents it from collapsing into the nucleus. The wave nature that gives the electron its peculiar quantum identity is the very thing that ensures the stability of all matter. Without quantum mechanics, atoms couldn't exist. Without atoms, nothing we know could exist. The stability of the universe is a quantum mechanical phenomenon, and the electron is at the center of it. It's worth pausing to appreciate how strange this is from the perspective of everyday experience. We live in a world of solid objects, tables, chairs, floors, walls, buildings, mountains. Everything seems solid and stable and permanent. But all of it is made of atoms, and atoms are mostly empty space, with electrons existing as fuzzy probability clouds around tiny, dense nuclei. The solidity you feel when you press your hand against a table isn't because the atoms in your hand are touching the atoms in the table. It's because the electron clouds of those atoms repel each other through a combination of electromagnetic repulsion and a quantum mechanical effect called the Pauli exclusion principle. The Pauli exclusion principle, formulated by Wolfgang Pauli in 1925, states that no two fermions can occupy the same quantum state simultaneously. Electrons are fermions. This means no two electrons in the same atom can have exactly the same set of quantum numbers. This is why the periodic table has the structure it does. Electrons fill energy levels sequentially because each state can hold only a limited number of electrons. The exclusion principle also explains why matter has the volume it does. When you push atoms together, their electron clouds start to overlap. But the exclusion principle prevents the electrons from all piling into the same lowest energy state. Some electrons must occupy higher energy states, which require more space, This creates a pressure, called degeneracy pressure or Pauli repulsion, that resists further compression. This is not an electromagnetic force. It's a purely quantum mechanical effect arising from the antisymmetric nature of the fermionic wave function. Degeneracy pressure is what keeps white dwarf stars from collapsing under their own gravity. A white dwarf is the remnant of a dead star, about the mass of the Sun compressed to the size of the Earth. Gravity is pulling it inward, trying to crush it further. What holds it up is the Pauli exclusion principle acting on its electrons. The electrons cannot all be squeezed into the lowest energy state. They resist compression, creating a pressure that balances gravity. Without quantum mechanics, without the exclusion principle, white dwarfs would collapse. And the same principle, operating at the atomic scale, is why ordinary matter has rigidity and volume, why tables are solid, why your hand doesn't pass through the table when you place it down. So the quantum mechanics of the electron doesn't just explain why atoms are stable, it explains why matter has the properties it does. Solidity, rigidity, volume, the entire macroscopic world of tangible objects arises from quantum effects operating at the atomic scale. The electron's wave nature, the uncertainty principle, the exclusion principle. These aren't abstract theoretical curiosities, they're the foundations of material reality. And yet, despite everything we know about the electron, despite the extraordinary precision of QED, despite the success of the Standard Model, profound mysteries remain. Why does the electron exist at all? Why is there an electron field permeating the universe? The Standard Model doesn't answer this. It takes the existence of its fields as given and describes how they interact. But it doesn't explain why these particular fields exist rather than others, why there is an electron field, but not some other field with different properties. The Standard Model is a description, not an explanation, of the particle content of the universe. Why does the electron have the mass it has? The Higgs mechanism explains how the electron acquires mass through its interaction with the Higgs field. But it doesn't explain why the coupling between the electron field and the Higgs field has the particular value it does. That value is a free parameter, measured but not predicted. It's one of the inputs to the theory, not one of its outputs. A truly fundamental theory would predict the electron's mass from first principles, derive it from something deeper. No current theory does this. Why are there 3 generations of matter? The electron is the lightest charged lepton. The muon is the same thing, but 207 times heavier. The tau is the same thing, but 3,477 times heavier. Each generation is a carbon copy of the previous one, but heavier. The Standard Model accommodates this, but doesn't explain it. When the muon was discovered in 1936, the physicist Isidore Isaac Rabi famously asked, "Who ordered that?" Nearly 90 years later, we still don't know. No one has explained why nature repeats the same pattern 3 times at 3 different mass scales. Is there a symmetry reason? Is there a deeper structure? Are there more generations we haven't discovered yet? We don't know. Why is the electron's charge exactly equal in magnitude to the proton's charge? The proton is made of 3 quarks, each carrying a fractional charge of plus 2/3 or minus 1/3 the electron's charge. The total comes to exactly plus 1, perfectly balancing the electron's minus 1. But the quarks and the electron are very different particles described by different fields. In the Standard Model, there's no fundamental reason their charges must balance so precisely. Grand unified theories can explain this by placing quarks and leptons in the same mathematical structure, but grand unification hasn't been confirmed. These are not minor loose ends, they're deep, fundamental questions about the nature of reality, and they all connect to the electron, this seemingly simple particle that turns out to be a window into the deepest layers of physics. The electron is perhaps the best studied object in the history of science. We know its properties with extraordinary precision. We can predict its behavior in almost any situation. And yet, at the most fundamental level, we still don't fully understand why it is the way it is. Let me end where we began, with a question that sounds like it should have a simple answer, but doesn't. What is an electron actually made of? And why can't it fall into the nucleus? The answer to the first question is that the electron, as far as we can tell, isn't made of anything. It's fundamental. It's an excitation of a quantum field, a basic feature of the universe that doesn't decompose into smaller parts. Its properties, mass, charge, and spin, are described with breathtaking precision by quantum electrodynamics, but the ultimate origin of those properties remains unknown. The electron is one of nature's irreducible building blocks, and we don't yet know why it has the particular characteristics it does. The answer to the second question is that the electron doesn't fall into the nucleus because quantum mechanics won't allow it. The electron in an atom is not a tiny ball orbiting a central nucleus. It's a quantum entity described by a wave function, existing in one of a set of discrete allowed energy states. The lowest state, the ground state, has a finite energy and a finite spatial extent. The uncertainty principle guarantees that confining the electron closer to the nucleus would increase its kinetic energy by more than the potential energy gained from being closer. The ground state represents the optimal balance, and below it there is no further state to transition to. The electron can't fall into the nucleus because the quantum structure of reality has a flaw. The electron is already on it. These two answers are deeply connected. The electron doesn't fall in because it's a quantum object, and quantum objects don't behave the way classical intuition suggests. They don't have trajectories, they don't spiral, they exist in states, and those states are governed by mathematical rules that have no classical parallel. The stability of atoms, the existence of chemistry, the solidity of matter, the structure of the periodic table, the functioning of stars, the existence of life, all of it traces back to the quantum nature of the electron and the principles that govern its behavior. A century ago, physicists looked at the atom and saw a paradox. The electron should fall into the nucleus. Classical physics demanded it. The atom should be impossible, and yet atoms exist. They exist by the trillions of trillions of trillions, forming every structure in the visible universe. The resolution of this paradox required a revolution in our understanding of nature, a revolution that replaced the deterministic, continuous, intuitive world of classical physics with the probabilistic, quantized, deeply counterintuitive world of quantum mechanics. That revolution is arguably the greatest intellectual achievement in human history. It began with Planck's quanta in 1900. It continued through Einstein's photons, Bohr's atomic model, de Broglie's matter waves, Heisenberg's uncertainty principle, Schrödinger's wave equation, Dirac's relativistic electron theory, and the development of quantum field theory and the Standard Model. Each step built on the previous ones. Each step revealed deeper layers of reality. And at every step, the electron was there, at the center of the story. The particle whose behavior forced physicists to abandon one classical assumption after another, until they arrived at a picture of reality that none of them could have anticipated. The electron is tiny, it's fundamental, it's quantum, and it's the reason you exist. Every atom in your body is stable because of the quantum mechanics of electrons. Every chemical bond that holds your molecules together is formed by electrons. Every electrical signal in your brain is carried by electrons. The light you see is emitted and absorbed by electrons transitioning between energy levels. The solid ground beneath your feet is solid because of the electron's quantum properties. You are, in a very real sense, a structure built by electrons, and those electrons are governed by laws that are nothing like the laws of everyday experience. They're governed by probability, by uncertainty, by quantization, by the wave nature of matter. Laws that seem strange and counterintuitive when you first encounter them, but laws that produce a universe of extraordinary richness and complexity. A universe of atoms and molecules and stars and planets and life and consciousness. All of it arising from quantum mechanics. All of it made possible by the fact that electrons don't fall into nuclei. The next time you look at your hand, remember what's happening at the atomic scale. Trillions upon trillions of electrons, each one a quantum excitation of a field that fills the entire universe, each one existing as a probability cloud around a tiny nucleus, each one occupying a specific quantum state determined by the Schrödinger equation and the Pauli exclusion principle. Not orbiting, not spinning, not following any path you could draw on paper, just existing, in the peculiar, irreducible way that quantum objects exist, holding your atoms together, giving your matter its structure, making you possible. That is what an electron is, and that is why it doesn't fall into the nucleus. The answer isn't simple, but it's beautiful, and it reveals something profound about the universe we live in. Beneath the familiar world of solid objects and predictable motion lies a deeper reality, governed by principles that challenge every intuition we have about how things should work. A reality where particles are waves, where certainty gives way to probability, where the act of measurement shapes what is measured, and where the stability of everything we know rests on quantum mechanical rules that nature follows with absolute, unyielding precision. That's the universe you live in, made of quantum fields, held together by quantum rules, more strange, more subtle, and more magnificent than anything the classical world could have imagined.